guys, what's the crack? So this video we're going to go over what an exoplanet is. So an exoplanet is a planet that's beyond our solar system, right? So we know in our solar system we have Mercury, we have Mars, we have Venus, you have Neptune. Okay, the order of the planets, if you've forgotten, is the way I remember it, is my very excited mother just showed us 9 planets, but she was lying because Pluto is no longer a planet. So those are all the planets in our solar system. We have Mercury, you have Venus, you have Earth, you have Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, so what an exoplanet is a planet outside of our solar system. A planet that's orbiting a different star. And today, well, we nearly today have over 6,000 confirmed exoplanets. So think there's the planets we know of in our solar system, more than 6,000 now. And when I was in school studying, we only basically had around 500. So it's mad how many we've discovered. And we basically now think that nearly every star in the sky probably has its own planet orbiting it, its own exoplanet. So how do we detect these? First thing is direct observation is really difficult. So direct observation is when you have on your Earth, we have some telescope and we're basically looking at the stars trying to see if we can see that there is a planet orbiting that star. But it's very hard to see because if the star is really bright, that star or that light from that star is going to obscure all of the light that's been reflected from its planet. So it's really hard to see. Also, our telescopes might not have a good enough resolution. So they might not be able to see them as the two separate objects. So because of the resolution of our telescope being poor or not good enough, or because the star is very bright, we might not be able to see that exoplanet that's orbiting it. So direct observation of your telescope is quite hard. So that's why we had these two other methods called the transit method and the radial velocity method. So the transit method, what that one is let's say we have our star and we've got a planet that's going to orbit that star, our exoplanet, okay? So let's say we're on Earth here looking up that telescope at the star, we're looking at the light from the star. We can see that when the planet is over here, and it's not in front of the star at all, so I just rub out this line so we can see what I'm talking about. When the planet's over here, the light that we're going to receive from the star is going to be extremely bright, extremely bright, extremely bright. As the exoplanet moves towards it, the light's still extremely bright because we're getting all of that light from that star onto our telescope. But as that planet starts to cover that star, we're blocking a bit of that star's light reaching us. So we get a dip in it. And as that planet continues to cross that star, we're going to keep getting a dip in that light curve until the star gets the other side. Until the planet, gets the other side. And then now, because the planet's on the other side, we're getting all the light again from that star hitting our telescope, so the intensity is high again. Okay. Something we need to do though is we need to reserve this for a really long time. Sometimes the orbit of that planet might be too long, so we'll never actually see if it's because of an orbit or not. Because this is not good enough to know if it's because there's an exoplanet here, or a planet orbiting that star, or just something passed in front of our telescope. So what we want to do is you want to observe it for a long time so we can see that there's these periodic dips in the light curve. So we can see that it is because of an orbit. Okay, but sometimes, again, that planet might be really, really far away from its star, so its orbital period might be really, really long, in which case you might have to wait years until you see it again. And maybe your telescope gets decommissioned or shut down before you get that other orbit. So that's one problem with the transit method. Another problem is, if we're looking here, we have to assume that, let's say the star is shining from my hand, we have to assume that the planet crosses in front of us, so it actually blocks some part of that star's light. Okay, so it has to be in the right, correct plane of orbit for us to observe that dip in that light. But not all planets are going to orbit that star in that same plane. They might orbit the star in a different plane. So you see, if it's orbited in this plane, it's never going to block any of that light from our star because it's orbiting in a different plane. So another problem with the transit method is that the only reason we can see these dips is that it has to be in the correct alignment for the transit to cross the path that our telescope can detect. So again, what we said is that our telescope is where the camera is right now. It would have to pass in front between where we are on Earth and where the star is, so we can see that dip in that light. But if it orbits in this rotation, we would never see any dip of that light. Okay, the other one then is called the radial velocity method. So this one is that if we've got a star and we have any type of exoplanet, what's going to happen is there's going to be a center of mass. So things don't always orbit the star, they orbit the common center of mass. Okay, so people might think that all these planets orbit the sun, but they orbit the center of mass. And it's just because the sun is so big compared to those planets, the center of mass is within the own radius of the sun, so it doesn't really seem like the sun moves. So again, what we're saying is we've got our star and we've got our planet. And what's going to happen is they're going to orbit a common center of mass. So let's say it's quite a large planet. Let's say the center of mass is here. So again, what's going to happen is our star is going to orbit that common center of mass, and our planet is also going to orbit that common center of mass. So what we do down on Earth is that we use our telescope again to look at the light from the star. And what we can see is the star is going to be parts of it moving towards us and parts of it parallel to us and parts of it away from us. And what's going to happen then is when the star is moving towards us, that means the light is going to be slightly blue shifted. And when the star is moving away from us, the light we receive from the star is going to be slightly red shifted. So what we can see is, as we observe this light from the star, we can see that it's going to have light from the stars here, just coming straight down at us. That's fine because it's moving parallel to us. So that's going to be one wavelength. This wavelength here is going to be slightly shorter, and this wavelength here is going to be slightly longer. So what we can see is the star seems to slightly wobble, and it's because of that Doppler effect, because it's caused to be orbit a common center of mass because there are some planets there. So again, the only reason the star would wobble or seem to have this Doppler effect is because there is a center of mass that's been shifted outside the center of its own sun, of their own star, because there's some other planets there or some exoplanets. Problem with this is, let's say, like we said before with our solar system, the star might be so much bigger than any of the planets, which means that when we look at the center of mass is within the own orbit, the own radius of the sun. So the sun will just orbit around that center of mass. So it just lifts very, very slightly. And that can be really, really hard to detect. So